This is an electron. Electrons are one of the particles that made up our universe. One of the key properties of these particles is their negative electric charge. A charge is just a number associated with each particle. You can imagine the charge as this orange sphere around the electron. Greater is the charge, the bigger the sphere is. The sphere is responsible for the bending of the electric field. The two-dimensional electric field can be imagined as this white sheet. When no charges are present, it remains perfectly flat and static. It's quite boring. Let's insert our friend the electron in this two-dimensional space. Space bends, creating a small hole under the electron. This hole becomes bigger if the electron charge increases, and it shrinks if the charge decreases. The color and the curvature of the sheet let you better understand the strength of the field. If instead of a negative particle you use a proton or a positron characterized by a positive charge, then the paper bends upward. Let's now consider a bigger area around the charged particle. What happens if we continuously vary the charge from negative to positive value and vice versa? It will take some time for the information to arrive at the edge of our two-dimensional field. As you can see, information travels in waves or oscillation of the electric field. Those waves are what we generally call lights. In reality, electrons and positrons maintain their charge forever, so this representation is not correct. But it's possible to obtain the same result considering a couple of particles, one positive and one negative, that oscillates back and forth asynchronously. Do you notice that the weight generated starts to behave like lines far from the center? If we consider a three-dimensional world, those lines are indeed planes that propagate in a certain direction, and for this reason they are called plane waves. Plane waves are very important in the description of a lot of electromagnetic phenomena. Let's consider a new situation. A torch is switched on to illuminate the environment. The light emitted by the torch can be easily represented by plane waves. Those plane waves continue forward their journey until they reach a wall. At this point, a bright circle appears on the wall. If we rotate the torch, we will change the direction of propagation of the plane waves that will so illuminate another point on the wall. To better understand what is going on, I can show only the field with an amplitude bigger than a threshold. In this way, all the trash due to numerical approximation is eliminated and we end up with a clean straight line. What happens now if I place a metallic body in front of the light? The electric field can penetrate a lot inside the body, and so the radiation is reflected. Close to the body, we can experience the interference pattern between the incoming wave and the reflected wave. After this small region, the plane wave continues to propagate in the new direction that follows the reflection law. The angle of the reflected ray is equal to the angle of the incoming ray, in respect to the normal of our material. This is visible also in this example, in which I prepare the obstacle in a different orientation. We can take a lot of different experiments with this new setup, but for today it's enough. As usual, you can find in the description the link to the script as well as a link to CAVLab that helps me a lot in the math. Nature always surpasses my imagination.